Hello guys, I'm Prakriti from CSEI studying in Sri Venkateshwar College of Engineering. Today I'm going to present about pumping lemma and its application, which comes under the topic called automated theory and compiler. Contents are Introduction to ATC, pumping lemma, applications of pumping lemma, and conclusion. Introduction to ATC, Automated Theory. Automated theory is a branch of theoretical computer science that studies abstract machines or computational models and their capabilities. These abstract machines are called automata and they are used to understand and describe the behavior of algorithms and computations. Automata theory is the fundamental to various areas of computer science, including formal languages, compilers, artificial intelligence, and more. Key concepts include automation types, finite automata, simple machines with a finite set of states used to recognize regular languages, pushdown automata, extension of finite automata with a stacked memory used for context-free languages, Turing machines, theoretical computing devices with an infinite tape used to understand general algorithms. Formal languages, regular languages described by regular expressions and recognized by finite automata. Context-free languages, described by context-free grammars and recognized by pushdown automata. Applications of automata theory is compiler design. Automata theory is a crucial for designing lexical analysis, that is kernels, and parsing the syntax of programming languages. Software engineering used in software verification, model checking, and designing algorithms. Compiler. A compiler is a specialized software program that translates high-level source code written in one programming language into a lower-level target language, typically machine code or an intermediate code. The complication process involves several stages, with each stage performed by a specific component of the compiler. Key components and stages include lexer, that is scanner. The task of lexer is breaks the source code into tokens. Use of automata theory, regular expressions and finite automata are employed to define the lexical structure of programming languages. Semantic analysis. Task checks the meaning of the statements and expressions in the code. Use of automata theory may involve additional formal methods to ensure semantic correctness. Intermediate code generator. Task is translates the source code into an intermediate representation. Use of automata theory focuses on generating an intermediate code that captures the essential semantics of the source code. Or optimization task enhances the efficiency of the intermediate code. Use of automata theory may involve various algorithms of heuristics to optimize the code. Code generation task translates the optimized intermediate code into the target machine code. Use of automata theory involves gathering efficient machine code instructions. Code optimization task of the code optimization is further improves the efficiency of generated machine code. Use of automata theory may involve advanced algorithms and optimizations. Pumping lemma. The pumping lemma is a fundamental tool in the field of formal language theory, particularly in the context of proving that certain languages are not regular. It provides a set of conditions that any regular language must satisfy, and it is used to demonstrate the limitations of regular languages. The pumping lemma is an essential part of the theoretical foundation for understanding the distinctions between regular languages and more complex language classes. Purpose of pumping lemma. The pumping lemma serve as a criterion for regular languages, helping to identify patterns that our regular languages share. It provides a means to prove that a language is not regular by demonstrating that certain strings in the language cannot satisfy the conditions set by the lemma. Clarification is it's important to note that while the pumping lemma provides a powerful tool for proving the non-regularity for certain language, Not all non-regular languages can be proven, such using the pumping lemma. Additionally, there are languages that satisfy the pumping lemma but are not regular. The pumping lemma is specifically applicable to regular languages. The pumping lemma is commonly used in proofs to show that a particular language is not regular. The general structure of proof using the pumping lemma involves assuming, for the sake of contradiction, that the language is regular and the demonstrating the conditions of pumping lemma are violated. Here's a step-by-step guide on how the pumping lemma is typically used in proofs. Steps in using the pumping lemma in proofs. Assumption: start by assuming the language is regular. Suppose L is a language, and for the purpose of the proof, assume L is regular. Selection of a string: choose a representative string for the language. Select a specific string S from L that is sufficiently long. Application of pumping lemma: express the string as S is equals to XYZ. According to pumping lemma, S can be decomposed into three parts, that is XYZ, such that XY is lesser than or equals to P, Y is greater than 0, and XY to the power I Z belongs to L for any non-negative integer I. Consider all possible decompositions. Consider all possible ways to decompose S. Analyze the different cases for decomposing S is equals to XYZ based on the conditions of the pumping lemma. Show a contradiction. Demonstrate that for any decomposition a contradiction arises. Show that there exists an I for which XY to the power I Z is not in L. This often involves demonstrating that XY to the power I Z violates some property that all strings in L should satisfy. Conclude the non-regularity. Conclude that the assumption of regularity leads to a contradiction. Since the assumption that L is regular results in a contradiction, the conclusion is that L is not a regular language. Applications of pumping lemma. Proving non-regularity. The primary and most direct applications of the pumping lemma is to prove that a given language is not regular by assuming the language is regular and then showing a contradiction based on the pumping lemma conditions. One can establish that the language does not meet the criteria of the regularity. Theoretical boundaries of regular languages. The pumping lemma helps define the boundaries of regular language. It highlights the limitations of finite automata in recognizing certain patterns within languages and provides insights into the types of languages that go beyond regularity. Educational tool. The pumping lemma is commonly used in educational settings to teach students about formal language theory and the distinctions between regular and non-regular languages. It serves as a foundational concept in theoretical computer science courses. Language hierarchy. The pumping lemma contributes to the understanding of the Chomsky hierarchy, a classification of formal languages. Regular languages from the lowest level in this hierarchy, and the pumping lemma helps to identify languages that belong to the higher levels. Compiler design. In the context of compiler design, the pumping lemma is employed to show that certain languages cannot be described by regular expressions or recognized by finite automata. This information is valuable in designing lexical analyzers and phrases of programming languages. Algorithm design. The limitations imposed by the pumping lemma on regular languages influence algorithm design and complexity analysis. Understanding the distinction between regular and non-regular language is crucial when designing algorithms for pattern matching, string manipulation, and language processing. Research in formal language theory. The pumping lemma has inspired further research and development in formal language theory. It motivates investigations into more complex language classes and the development of advanced models of computation. In conclusion, the pumping lemma is a pivotal concept in the realm of formal language theory, providing a systematic method for proving the non-regularity of languages. Its applications extend beyond theoretical consideration and play a significant role in practical fields such as compiler design, algorithm analysis, and the foundational understanding of computational complexity. The pumping lemma stands as a cornerstone in the theoretical underpinnings of computer science, guiding our understanding of the capabilities and limitations of finite automata. Its influence extends to various aspects of computational theory and practical applications, making it a fundamental concept for students, researchers, and practitioners in the field.